Okay, welcome everyone to this week's One World IAMP Mathematical Physics Seminar. It's great to see you all here. This talk, as all of our talks, is being recorded, and you can watch it in your own time on our YouTube channel. If you want to find out more about IAMP, if this is your first time watching our seminar, there is some information in the chat, or if you're watching it on YouTube, there is some information on the website as well. So if you're interested in following this seminar, you can join our mailing list to find out about ongoing talks. All right, but now let's get to the actual talk. It is my great pleasure to welcome Viet Dang, and he's going to talk about the Phi43 measure on compact Riemannian manifolds. Viet, the floor is yours.
Okay, thank you. So first, I would like to thank the organizers for inviting me to this impressive seminar. It's a real honor. So today I'm going to talk about the Phi43 measure on compact Riemannian manifolds. So this is first a joint work with To, so a colleague from Sorbonne University, Ismaël Bailleul from University of Brest, and Léonard Ferdinand, who is a PhD student of Vincent Rivasseau at Orsay. So my talk will be divided into two parts. So in the first part, I will discuss Feynman graphs and use as a context the perturbative Phi43 theory. And the first part is just the motivation for the first part is to prove a power counting theorem that will play an important role because it allows to control analytical quantities that will appear in the second part, where we will construct the Phi43 theory non-perturbatively as some invariant measure of a certain dynamics. Okay, so let me start very smoothly. So I am going to give you a glimpse of what is a Feynman graph and where it could come from. So in one sentence, correlators of quantum field theory in the perturbative regime can always be expanded as sums over Feynman amplitudes. So let me give you an example in our which is relevant in our context. So I'm going to talk about the Phi43 theory. Yeah.
So here the coupling constant G is positive, said to be positive, right? The coupling constant G,
but
it is positive, right?
Yeah. But it's perturbative. This first part is perturbative, so G is like a formal parameter. And so the data for a Phi43 theory is a formal parameter G that I write in red, that is called the coupling constant. And you need a background. So here is the 3 torus, it's your space, okay? And your fields are going to live like they are functions on your space formally. The data you need to start with is
I expect that.
Yeah.
I expect that you're going to like make sense of some kind of Borel summation. No, not here.
No, not here. Unfortunately, not here. These tools and everything I'm going to talk about is not going to make sense of Borel summation. Okay, so let me continue. So I start from an action functional. So it's a functional of the field phi. So phi is a function on your 3 torus. It's a sum of a quadratic part in the field phi, which is the Dirichlet energy. So this is often called the free part in QFT textbook, plus your coupling constant times the integral of phi to the 4 over the torus T3. So this integral of phi to the 4 over the torus T3 is often called the interaction. And we want to make sense of the formal measure e to the power minus s divided by the partition function. So I write this as a bit like a Gibbs measure in statistical mechanics. And a quantity, a natural quantity you would like to consider is, recall you are in your 3 torus, you consider 2 points, x and y, and you consider the value of your field over these 2 points, phi x and phi y, and you would like to consider the average of the product of the value of the fields, and the average is taken with respect to this formal measure. I say formal because the coupling constant here is like a formal variable. It's not an actual number. And what you can prove is that this average, this 2-point function, can be expanded as a formal power series in G, so in the coupling constant, in powers of the coupling constant, and each term in this power series can be written formally as a product of green function of the massive Laplacian. So by green function, so what I denote by capital G, X, Y is the Schwarz kernel of the inverse of the massive Laplacian. And so you have here formal products of green function.
You missed the minus sign in front of Laplacian.
I'm sorry, I take the positive Laplacian. I'm sorry. I have this convention. I like to use so my Laplacian is minus dx squared. Is it okay? You agree?
Yeah, I think we could maybe postpone the more technical questions to after the talk, so we'll be ample time to actually ask about the details, if that's okay.
No problem. Anyways, so this Laplacian is a minus sum of the square derivatives, so that is positive. Okay, so and these formal products of green functions, they are integrated on copies of your based manifold, your torus T3. Okay, and these amplitudes, these formal product of green functions, they can sometimes be represented pictorially by these diagrams. And these diagrams are what people call Feynman diagrams. So for the moment, don't worry. I just give you this formula to give you a flavor. And in the next slides, I'm going to define a little bit more rigorously, give a definition of the Feynman amplitudes. And I just would like to make a remark is that these Feynman diagrams, they appeared historically in the study of quantum electrodynamics, which is the quantum field theory studying the interaction of electron and photons. And for instance, this diagram that I draw here, it represents a process involving the electron, positron, and photon. And so this is a diagram coming from what people call Baba scattering. So it has a physical meaning. That's what I mean by these diagrams. They really represent interaction processes between particles in quantum field theory. Okay, so now let's go back to pure math. We forget about the motivation. I can present these Feynman rules in some kind of axiomatic way as a correspondence between pictures and formal products that I can make with the green function. So for each vertex in the graph, you can think that you associate to each vertex a point on your manifold. For each edge of the graph, so here I have this edge connecting this vertex in purple and vertex in red, I associate a green kernel, GXY. If you have several edges that are glued together at a common vertex, you can think of this, you can associate a product of green function, which has one common variable and which are multiplied. So if you think about this very intuitively, if you have, for instance, 4 edges connecting 2 vertices, you can associate to this a power of the green function. And the last step that I need to present in these rules is that if I draw you a graph, then in a graph you have internal vertices. In this graph, for instance, you have 2 red internal vertices, and you have external vertices that I denote in purple. Then you will need to integrate the variables that correspond to the internal vertices. For instance, this graph has 2 internal vertices in red. And so it means that you have to integrate this formal product of green functions over 2 copies of your 3 torus. Okay. So now that I have presented these Feynman rules, what I can tell you is that in Phi4 theory, perturbative Phi4 theory, all the interaction vertices that appear in your graphs, they have multiplicity 4. Let me go back to the previous picture. You see, this interaction vertex has multiplicity 4. This one also has multiplicity 4. This comes from the phi to the power 4 that we have in the Lagrangian. You see, when we started at the very beginning, the action functional had this interaction term with the phi to the power 4. And this dictates the combinatorics of the graphs that you encounter in perturbation theory. Okay, so now I want to come to the main theorem of the first part of my talk, which I call baby power counting. So it's a baby case of one of the main tools we are using in our paper to control Feynman amplitudes for the SPDE. But here I would like to present a much simplified version of what we are using in the context of perturbative Phi43. Okay, so this is reminiscent. This is very closely related to the power counting theorem of Weinberg in 1960. So you consider MG a smooth, closed, compact Riemannian manifold of dimension D. If you don't like manifolds, just say the torus TD. And you are given a graph, gamma, with no self-loops. And I denote by E gamma and V gamma the edges and vertices of the graph. And what the theorem says is if for all subgraphs, gamma prime of your original graph you started with, 2 times the number of edges minus the first Betti number of your graph, gamma primes times the dimension, is greater than 0, if for all subgraph this thing is satisfied, then your amplitude is in fact integrable. Like you can, I mean, the integral makes sense, is well defined. Otherwise, if for all strict subgraphs of your graph, this criterion is satisfied, but if for gamma itself, you're in the critical case, 2 times number of edges equals the first Betti numbers times D, then we call this graph primitively divergent. And the corresponding amplitude, so by amplitude, I mean the corresponding formal product of green function, is not going to be integrable. And what you'll need to do is you'll need to consider a smooth function on your configuration space. So this smooth function, C gamma epsilon, we can call it counter term. It blows up. It blows up when epsilon goes to 0 plus, and you will need to mollify your amplitude. So to each green function, you associate a mollified green function by, for instance, using the heat kernel, heat mollification. It gives you well-defined amplitude that depend on epsilon. This is the cutoff, like in quantum field theory, we call it the cutoff. And what we can prove is that if you take your amplitude, regularized amplitude, you subtract the counter terms times the delta distribution, which is supported by the deepest diagonal. So you see your amplitude A gamma, your amplitude A gamma, it lives on the configuration space M to the power of V gamma. So in this configuration space, I can give you a picture, like this is a configuration space, like M2, you have the deepest diagonal. It's when the 2 points collide. And this delta here is a distribution which is supported by the deepest diagonal. And what I claim is that if you take your regularized amplitude, you subtract this divergent counter terms times the delta distribution carried by the deepest diagonal, at the limit, you get a well-defined distribution on m to the power v gamma, and this distribution is the renormalized amplitude. So let me give you an example. I'm sorry if this definition and this formalism is a bit heavy. I'm going to give you an example. So when d equals to 3, for instance, if you consider this graph here, this graph is convergent. You can see, if you look at the criterion here, the Betty B1 equals to 1. You have one loop in your graph. And you can see that in d equals to 3, the following graph is, this is an example of primitively divergent graph. If you look at its subgraphs are going to converge. But if you look at this full graph here, it is going to diverge. So this graph here has a funny name. I don't know why it has this funny name, but it is called the sunset graph. And it plays an important role in the Phi43 theory, because it will describe one of the counter terms that you are going to subtract when you construct the Phi43 measure. Okay.
You certainly see the horizon and the sun there, right? I'm sorry.
Oh yeah. Probably this is why.
So think about the ocean and the sun setting into the ocean and reflecting.
Okay, I get it.
Very romantic.
I get it. Yeah. It's a romantic graph. So here is the ocean. Okay, so this is sunset graph. Okay, it is really the typical example of primitively divergent graph in d equals to 3. Okay, so okay, so now let me sketch the proof of this theorem, this baby theorem. So the first idea behind this theorem and behind many works in singular stochastic PDE is that you need to use scaling to probe singularities. You have analytical objects, functions, distributions, and you make scaling, you zoom infinitesimally near some singular regions, and you see how the object responds when you zoom. This gives you singularity exponents, and these exponents, they measure the singular behavior of your objects near the singular locus. So let me be much more precise. You look at the x and y, so 2 points in your, let's say in your torus, you're in your torus T3, you have 2 points, and you can scale y so that it gets close to x. How do you do it? You multiply y minus x by lambda plus x, and when you let lambda goes to 0, this point, lambda y minus x plus x, will collapse to the point x. So here I represent pictorially in the configuration space. So this is the configuration space of 2 points. You have the diagonal when x equals to y, and this scaling will collapse the whole configuration space to the diagonal x equals to y. Okay, so now that you have defined the scaling, you can define a scaling operator that acts on the green function by exactly collapsing the point y. The second argument, it is going to collapse the second argument on the first one. Okay, and when you look at the size of the green function, when you scale it by a factor lambda, you see that you have a lambda to the power of 2 minus d, if it's the green function of the Laplacian in dimension d. So the singularity exponent associated to the green function is 2 minus d. Okay, so this idea of scaling distributions, scaling objects, I think it goes back to, I don't know, very long time in analysis, but very closely related to what I'm talking about. It appears in the work of Yves Meyer in 1998, and also in the work of Brunetti Fredenhagen around 2000. So since in the sequel, I'm going to work on manifolds. So in the manifold setting, you need to be more careful about the way in which you scale your objects. And for this, you need to introduce Euler fields to scale points on manifolds, to scale towards a singular submanifold. And these Euler fields were introduced independently by many authors. But here, since I'm in the toy model, I don't want to spend too much time on these Euler fields. So let me now state the theorem that is the main tool that we are going to use inductively to prove the baby power counting theorem. So this is a kind of abstract theorem, and it can be formulated as follows. You are given an ambient manifold X. So you have a big manifold X. You have a submanifold that I denote by Y. It's a submanifold in big X. And you are given a function F. You are given a function F, which is in L1 of X minus some tube. You all see there is a tube around Y. I have a tube around Y. I remove the tube, and I have a function F, which is integrable in the complement of the tube. Now, if when I scale my function F by a factor lambda, so I zoom by a factor lambda, which goes to 0. And if I look at the L1 norm of my zoomed F, L1 norm on X minus the tube, if this grows like lambda to the power S, then this gives me, so this is an assumption of my theorem. So I assume that my F has this S as scaling exponent. So when I zoom F by the scaling, its L1 norm grows like lambda to the power S. So I have two cases. Either the exponent S, the singular exponent S here, is greater than minus the codimension of Y. So you see you have your Y submanifold. It's a submanifold, so it has a codimension. If the singularity exponent is greater than minus the codimension, then your F, which was a function which was well defined in the complement of X, it is well defined. In fact, it extends uniquely as a L1 function on the whole space. In fact, it's integrable on the whole space. And if in the critical case, if Fs is equal to minus the codimension of the submanifold Y, then you need to mollify your F. And so there is a mollified F that converges to F in L1 of X minus Y. And there is a counter term. And there is such that when you take the mollified F, you subtract the counter term. So this is a divergent counter term. It blows up when epsilon goes to 0 plus. And when you subtract this divergent counter terms, like the delta distribution on Y, this converges to a distribution on your whole manifold. And I want to insist your distribution, it is not a L1 function. Not a function. It is really a distribution. Let me give you an example. So first, for those who know, this is closely related to what people call Hadamard finite parts. So this is a very classical renormalization method in analysis. It's not in quantum field theory, it's in analysis. It appeared at the beginning of the 20th century in the work of Hadamard on the wave equation. So, and the simplest example of this theorem, you just consider x to the power s times the indicator function of x greater or equal to 0. So this is a kind of function defined on the half, supported on the half line, and you have your exponent s, and the submanifold y here is just the origin. Your stuff, it blows up at the origin, so y is 0. And your ambient manifold is the real line, it's R. So you see that if your exponent s is strictly greater than minus the codimension of the point, so you all know the codimension of the point is 1, so if s is greater than minus 1, then it's good. X to the power s indicator is Riemann integrable. Okay? So this is really what the theorem is telling you, is that in some sense, if s is bigger than minus the codimension, so you're Riemann integrable. And if s is exactly equal to minus 1, you have a problem. This thing here is never going to be Riemann integrable. But then if you have to do something. And so what you do usually is that you subtract something, you multiply by indicator of greater than epsilon, you subtract log epsilon times some constant times the delta of 0, and this converges when epsilon goes to 0 plus to what people call the finite part of x minus 1, indicator of the real positive real line. Okay, so in fact this is really a kind of very naive generalization of Hadamard's finite parts. Okay, so now just a comment. In our work and also in the Brunetti, Friedenhagen's work, when you renormalize the Feynman amplitude in Lorentzian manifolds, or when you renormalize the amplitudes for stochastic PDE, it's more complicated. You have to use microlocal analysis to control the size of your objects. You see here, since it's a toy model, I just use L1 norms to control objects. Here, I use a L1 norm, but in fact, in practice, for QFT purpose, you have to use more sophisticated norms or semi norms, but it is not relevant for this kind of example. I just wanted to make a remark. So what I'm going to do is that I'm going to apply this theorem that I just explained to you, the extension theorem, inductively on my Feynman amplitudes. So my Feynman amplitudes is a big distribution or a big function in my configuration space, m to the power of v gamma. So it's many points in M. And what I will do is that I will make an inductive extension when first 2 points collide, then 3 points collide, 4 points collide, etc. And at the end, when all the points, they collide together to the deepest diagonal, exactly in this order. So you make this induction. So intuitively, it means that to control the integrability of the amplitude associated to a graph, I'm going to first study the integrability of all the subgraphs. You see, I have this graph here. I look at all the possible subgraphs, and I look at the integrability of all the possible subgraphs. And so it means that I treat collision of the points to lower diagonals. And at the end, I will study the singular behavior of the Feynman amplitude when all the points, they collide together. Okay, so now let's be a bit more precise. So as I told you, I make the induction on the number of points. When there are only 2 points, the graphs are very simple. When you have only 2 points in your Feynman graphs, all the possible graphs is just multiple edges. And then you can see that the theorem is obvious for graphs with only 2 vertices. Because you know the singular behavior of the green function, it blows up like x minus y to the power 2 minus d. So it's very easy to verify the theorem when you have 2 vertices. Now you assume by induction but that your theorem holds true for all the possible Feynman graphs with n vertices. And you want to prove that then it holds true to all possible Feynman graphs with n plus 1 vertices. So since it would be too complicated to write the proof in general, I will present you the idea in an example. So I start with this graph. So in my example, n equals to 3. So I suppose that all the graphs that you give me that have 3 vertices, my theorem holds true. And now I give you a graph with 4 vertices. And in this graph with 4 vertices, I will try to prove that in fact this graph is integrable. So how do I proceed? I use first a simple idea is that I say that outside the region where the 4 points that correspond to the 4 vertices of the graph, they collide together. So outside this region, I can partition my configuration space into subregions. So here I give you an example of a subregion. So in this subregion, the point 1 and the point 2, they can collide together. The point 3 and the point 4, they can collide together. But no points here can collide with a point here on the right. You see, the points 1, 2 cannot collide with a point in the group 3, 4. And in such region is denoted by C 1, 2, 3, 4. So I kind of partition my point labels in subsets where the points in a given subset, they can meet together, but the points in different subsets, they can never collide together. Okay, so now you can cover the complement of the configuration space of 4 points, because here in your Feynman graph, you have 4 points. You can cover the complement by these strange regions where you have some group of points that are forbidden to collide. And now you study your Feynman amplitude, for instance, in this region, C1, 2, 3, 4. You look straight into the eye of your Feynman amplitude. You see that in this region, the point 1 and the point 2, they can collide. And this subgraph here, it's a graph which has 2 vertices, and it satisfies the assumption of the theorem. So the amplitude here, it is L1. In this subgraph here, the point 3 and the point 4, they can collide. And this subgraph, by the induction assumption, it is L1. And now you will ask me, yeah, but what happens if the point 1 and the point 3, they collide? It's not possible, because in this region, I forbid the points in this group to meet the points in the group on the right. So in this region, the green function that I represent in purple, that connect 1 and 3 and that connect 2 and 4, they are smooth because you take the green function outside the diagonal. So the green function of the Laplacian outside the diagonal is smooth. So there is no problem. So what I just tried to convince you is that outside the deep diagonal, because of the inductive assumption, your amplitude A is well defined. So this is, I summarize. So I take a partition of unity, which is subordinated to my cover, and then I write my amplitude A as a sum, which is indexed by the partition of unity. And on the right-hand side, everything is well defined on the configuration space M4 minus the deepest diagonal. And this is the moment where I apply the extension theorem. I apply the extension theorem where my submanifold Y is the deepest diagonal. My function F is this big thing on the right-hand side. And I see that under the assumption of the theorem that 2 times number of edges minus B1 times D is greater than 0, this assumption, due to the beautiful formula of Euler, so there is a formula of Euler that says that in a graph, the first Betti number is the number of edges minus the number of vertices plus 1. You use this Euler formula. From the assumption, you deduce that in fact the scaling exponent of the amplitude, is just the number of edges. So your amplitude here, you count the number of edges. So in the example of my graph, I have 1, 2, 3, 4, 8 edges. You multiply by the exponent of the green function, so 2 minus d. This gives you a number, and this number is the scaling exponent of the amplitude A of your graph, gamma. And this tells you that the scaling exponent of your graph A gamma is greater than minus the codimension of the deepest diagonal. And then you can apply the extension theorem, and it tells you that your amplitude is indeed integrable. Okay, so this finishes the sketch of proof of this power counting theorem. And in the critical case, if you are in the critical case, then you can see that the scaling exponent in the critical case is such that S equals minus the codimension. And in this case, you have to do the renormalization like in Hadamard finite parts. You have to subtract the divergent counter terms times the delta distribution of the diagonal. Okay. So this closes the first part of my talk. And in the time that I have left, I will go to the second part. And the second part is pretty independent. I mean, most of the second part is pretty independent of the first part. It's only at the end that I'm going to connect with the first part. So in the second part, I would like to go back to Phi43, but now in a non-perturbative way. I would like to view this Gibbs measure, this formal Gibbs measure that I wrote you at the beginning. So this E minus S divided by integral of d phi, E minus S phi d phi. I want to make sense of this as an invariant measure of some stochastic partial differential equation. So to motivate how we are going to do this, I'll go back to something very concrete. I'll go back to an example of a spin system, a discrete Ginzburg-Landau model. So assume that you have a discrete box. The discrete box I denoted by a big lambda. And on this discrete box, you have a lattice site. You have this lattice site in your discrete box. It's in epsilon ZD, discrete box. And over each lattice site, there is a spin. And the configuration, so the spin takes value in R. It's an R-valued spin. And your spin are connected by springs. You have so these elastic springs between neighboring spins. It will describe a kind of nearest neighbor interaction between your spins. So you are given an action for your spin system, and the action, it's exactly like in the continuum case. It reads as the sum of the discrete Dirichlet energy. So you see here you have the sum over sigma I minus sigma j square. So this is the analog, the discrete analog of integral of nabla phi square. This is the discrete analog of integral of m square phi square over lambda. And this thing here is just plus integral of a lambda of a polynomial of the field phi. So this is the interaction. So you just take some polynomial bounded from below, and you take P of your spins. And okay, just a comment. If you had no interaction, it is just a system of particles connected by springs, massive particles. But if you switch on the interaction, so what I call the interaction is this part, interaction in the sense of quantum field theory, then it means that your particles are kind of submitted to some potential, and they have preferred rest position. And the preferred rest position of your particles corresponds to the minimum of your polynomial, so minimum of your potential. So you look at the minima of the polynomial P, and this gives you preferred regions where your spins, they would like to stay. And so for instance, in the example of the polynomial 1 minus x square here, it's a double well potential. So your particle likes to be in here and in here, the two bottoms of the well. So now you consider the Gibbs measure on r to the power lambda. So r to the power lambda was the configuration space of your spin ensemble is so in QFT it's going to be the field space, and you consider this Gibbs measure. So here you are in finite dimension, so it's well defined. It's just it's given by exponential minus the action times a Lebesgue measure on r lambda divided by the partition function. And as above, one of the basic quantity you want to calculate, you want to make sense and calculate, define and then calculate, are the correlation functions. So these are just average of the product of the spins over different points, over k points, for instance. This is a k point correlator. So it's just the average of products of spins under the Gibbs measure. And more generally, given an observable, so it's a function over the configuration space of spins, you can also average your function against the Gibbs measure. So this is written like in statistical mechanics with these bracket symbols. So why are these Phi43 model and this Ginzburg model interesting from the mathematical physics point of view? From what I understand, they are interesting because they fall into the class of ferromagnetic spin systems. So here I give you a non-exhaustive list of ferromagnetic spin systems. So the most famous one is Ising model. The Ginzburg-Landau model without interaction, so without polynomial, is the discrete Gaussian free field. And the one we are interested in, so Phi43, sits in this class of ferromagnetic spin system, where you have a polynomial bounded from below, which gives you a potential. And these spin systems are interesting because they have the tendency to get the spin aligned in the same direction. Ising, Ginzburg-Landau, discrete Gaussian free field. And this is why they are called ferromagnetic, from what I understand. Okay, so now you want to define an operator, elliptic operator, and you want to define a semigroup associated to your elliptic operator. So P is the operator. The semigroup is E minus TP, such that the Gibbs measure is invariant under the dynamics generated by the semigroup. So this is okay. So this is the idea going back to the work of Parisi-Wu in the 80s. So in the example of the spin system, you just consider the Laplacian on r to the power lambda. So this Laplacian will play the role of a diffusion term, and the other term that you consider in your operator is the gradient of the action functional. So you have your operator P is a sum of a diffusion term plus a transport term. So the gradient S, it will play the role of transport. It will transport your measure to the minimum of the action functional. And there will be a competition between diffusion and transport. And what one can prove by a formal calculation is that the Gibbs measure is invariant under the semigroup generated by this operator P. So more formally, it means that if you are given an observable, a function f, which is continuous and bounded over your space of spin configurations, and if you consider the average of E minus TP acting on f, so you propagate f under your semigroup, you take the average under the Gibbs measure, is the same as the average of f under the Gibbs measure for all times t. So it means that your measure is really an invariant measure under your dynamics. And using this dynamics, it is a way to produce we'll see in just 2 slides, we'll see that we will be able to realize the Gibbs measure from the dynamics. In fact, we will generate the Gibbs measure from the dynamics. We'll go backwards. Here, in fact, I start from the Gibbs measure and I give you an operator whose dynamics leaves the measure invariant, but in 2 slides, I will go backwards. Okay, so I want to anticipate a bit in what will follow, since I want to take the continuum limit of my system when the lattice spacing goes to 0. My configuration space is no longer a finite dimensional vector space. At the end, my R lambda, when you let the mesh goes to 0, is going to be R infinity. And this is infinite dimensional. And the Laplacian that you see here, the Laplacian R lambda, it's not so clear how you can define it in infinite dimension and how you can study it. So it is more interesting to look at the process corresponding to the semigroup generated by the operator P. So I would like to recall, for instance, in the case of the heat equation, if you look at the heat semigroup acting on the function F evaluated at sigma, at a field configuration sigma, can be realized at the expectation. So you take your Brownian motion starting at sigma, and you stop it at time t, and you average over the Brownian motion starting at sigma and stopped at time t, and you also get the same value as on the left-hand side. So here on the right-hand side, you can say that the Brownian motion is the process that realizes your semigroup. And okay, so what you are going to ask me, so what is the process corresponding to the semigroup given by this operator, Laplacian plus the transport? So the answer is that you have to solve this stochastic differential equation, SDE, du plus gradient of S dt equals square root of dBi. So dBi is R lambda valued white noise. So B, if you want Bi are independent Brownian motion indexed by lattice site, and dBi is just independent white noise indexed by lattice site. So if you take U, a solution of this stochastic differential equation, this U is going to be random. You know why? Because on the right-hand side, this white noise is random. So the randomness comes from the right-hand side. Then the semi-group acting on F, evaluated at sigma, can be realized as an average of F of ut when you average with respect to the randomness coming from your SDE, coming from the white noise. So it's exactly the same picture as for the heat equation and for Brownian motion. And maybe for those of you who know, this operator P is very well known in mathematical physics. It's called Fokker-Planck operator. So it's very important. And in the context of spin chains, you can realize your Gibbs measure as a Birkhoff average. So here I want to write the name because it's so important. In fact, you can prove under good assumptions on your potential that the Gibbs measure, in the case of finite spin chain, is ergodic for the semi-group generated by P. And so by the Birkhoff ergodic theorem, you can trade as an average over all spin configurations by a time average. And so here you have a Birkhoff mean of the expectation of FUT. When times t goes to plus infinity, this is going to converge to the average of F against the Gibbs measure. So okay, so this works in finite dimension in this case of the spin system. And in infinite dimension, this is the only way we will have at our disposal to get, at the moment, the Phi43 measure on three-dimensional manifolds. So we will work with the stochastic process, and we'll try to prove a theorem on convergence of Birkhoff means, convergence of these quantities that are called Birkhoff means. Okay, so in the case the dimension d equals to 3, what we want is we want to take the scaling limit of your discrete box when the lattice spacing goes to 0. In fact, you want to take the continuum limit of the discrete continuum limit. So what does it mean to take the continuum limit? Is you want to ask, if you rescale in a proper way your correlation functions, do they converge at the continuum limit? And more generally, if you rescale the discrete fields, do they converge in low as random functions, random distributions? Exactly in the same way as if you, for the random walks, if you rescale random walks, do they converge in low to the Brownian motion? I mean, it's the same kind of questions. And the answer is yes. In fact, in dimension d equals to 2, and in dimension d equals to 3, on the 3 torus, or on the R3, or in the 2 torus in R2, these convergence were proved in the 60s and in the 70s. So by Nelson and Seagal for 2-dimensional models, and for 3D models by Klim and Jaffe in the 70s. In flat space, I want to insist in flat space. And here I give a list of many other contributors to this field that started with Nelson, Seagal, Klim, and Jaffe, which is called the constructive quantum field theory. So there are many people who did many contributions to the study of these quantum field theory measures. And one of the difficulties when you study these QFT measures is that the field phi does not exist as a random function, but it exists as a singular distribution. I'm going to give you a simple argument, but you can see also in the slides if you have them. You just calculate the dimension of the field phi. You do dimensional analysis. I mean, in physics textbook, they really love it. You say that the action functional has no dimension, and since the ddx has dimension d, has dimension length d, taking a nabla has dimension -1, you deduce that the length dimension of your field phi is 2 minus d over 2. So this tells you that in dimension d equals to 2, your field phi has no dimension, so you expect it to have regularity, Hölder-Sobolev regularity, c minus 0. And when d equals to 3, phi is an ugly object, and it has regularity -1/2 minus 0. So phi is a random distribution. It is expected to be a random distribution. And you see, this is the origin of the whole mess. Because in Phi43, let me go back to the beginning to show you the Phi43 action functional. We started with, you see the here you take a phi to the power 4, and I'm telling you that if the limit exists, you expect that the random phi is in c minus 1/2 minus 0, so it's a random distribution. So how come can you take the 4th power of a distribution? This is ill-defined. And this is the source of all the problems in QFT, constructive quantum field theory. I mean, in the whole subject of quantum field theory, is that you are taking powers of distributions, okay? And taking these powers of this distribution is ill-defined, and you have to do something to make it well-defined. And okay, so a natural question when you see these results by Glim and Jaffe in the 70s is that can you build such a Phi43 measure on manifolds? And in fact, in the math physics literature, there are many results on perturbative quantum field theory on manifolds. So here I give a list of many authors who define quantum field theory perturbatively on manifolds. And in fact, their results are more general than Phi43. In fact, these results that I'm quoting, in fact, usually they define Phi44 theory in d equals to 4. And even Yang-Mills, some work, there are some works on Yang-Mills 4, perturbative. And a natural question is that these Phi43 models, can you define them in a non-perturbative way on 3-dimensional manifolds? And this is an extremely natural question, at least to me. I mean, of course, you can say it is academic if you don't like manifolds, but for me, it sounded like a natural question. And so here I give you a list of, there are very few results in the literature where people are able to construct really constructively these quantum field theory measure on manifolds. And the only results I know are on surfaces for the Phi2 models. I give you some results. They are fairly recent, where they construct the Phi2 measure on surfaces for the Liouville conformal field theory. So this is the work of Guillermo Rod Vargas. So this is also on Riemann surfaces. The Gaussian free field. So this is the free theory. It's not interacting. So this exists in all dimension on all manifolds, compact manifolds. And the purpose of my talk is just to explain to you how we intend to build the Phi43 theory on all 3-dimensional manifolds. So what you do is, okay, so let me go back to the example of the SDE. When I had the spin chain, I considered the following SDE: du dt plus nabla s equals white noise, psi I over lambda. So now I would like to take a continuum version in perfect analogy, continuum version of the SDE. And this is going to be a SPDE, whose solution U will lives on R times M, and it reads, I write it exactly like the SDE, so that you, okay, if you are a physicist or if you try to read the physics textbook, I'm sorry, you have to write it that way. You replace the nabla by the functional derivatives, and you replace here is the white noise in time, Here it's the space-time white noise. Space-time white noise. So here you had a white noise for independent white noise for each lattice side. Here lattice sides become points in your manifolds. And so you have a space-time white noise. And this delta S over delta U, if you take S of U, the action functional of the Phi43 theory, if you take this action functional, then this reads du dt plus 1 minus Laplace u plus u to the cube equal psi tx. So this is really an SPDE, which I derived in perfect analogy with the SDE we saw above. So this is what you have to introduce in the manifold setting to be able to build your Phi43 measure. Okay. So here I wrote you the PDE dt phi plus p phi. P is 1 minus Laplacian equals minus phi to the cube. So it's like a nonlinear heat equation, but with a forcing term. This is the random forcing term. Okay. And you can define on compact manifold, you can define the white noise as a sum over the eigenvalues of the Laplace operator of psi lambda t. Psi lambda is a white noise in time. White noise in time. Times E lambda. E lambda is the eigenfunction of the massive Laplacian on your 3 manifold. So you have very simple definition of all the objects that appear in the SPDE. So now let me make a brief comment because my time is almost over on the difficulties so that you encounter trying to solve this SPDE. So what you do is that you make a formal fixed point argument on your SPDE. You write your formal fixed point argument, the first terms of the fixed point argument as the trees, and you're able to kind of estimate the regularity of the trees that appear in the formal expansion fixed point argument. And you see that there is a problem. I mean, basically you decompose your solution phi as a sum of 3 terms, and you look at the equation satisfied by the remainder. You expect that the remainder has certain good regularities. It is almost the C1 function, but still you see that the equation satisfied by this remainder has a problem, because in this equation you multiply something which is almost C1 by something which is almost C minus 1. So this is you have the product is ill-defined. And so to cure this ill-defined product, you will parameterize your solution using a Kohlhoff argument. You will parameterize your solution in the following way, where the new unknown u satisfies a new equation. This new equation. So in fact, this in this equation, yeah, I want to make a comment so that you can understand, at least have a flavor, is that this object that are pictorially represented as trees, they are random objects. They are stochastic, random stochastic objects that are constructed from the white noise psi. Okay, and the equation on the nice guy, on the u, on the term that I call u, in fact, it's also a nonlinear parabolic equation whose coefficients are singular. So the coefficients are the z0, z1, z2, this thing here, and this coefficient here. And these coefficients, they depend on a finite number of trees. So exactly this list of 6 trees. And these trees are some random stochastic objects that you will need to define stochastic objects that need to be defined by renormalization. So what I described in the first part, we use some renormalization inspired by what people do in perturbative Phi43 theory to give a meaning to this list of stochastic objects. So let me finish the talk by stating the main theorem that we prove. So what we prove is that if you mollify your noise by the heat kernel, so here you mollify your noise by applying the heat operator to it. I call it psi R, where R is your cutoff. So you have to modify your PDE. You have to subtract some singular counterterms, C1 and C2, that we calculate explicitly in terms of the cutoff R, such that at the limit, when R goes to 0, the solution of your mollified PDE converges to some well-defined solution of some renormalized stochastic PDE. And the solution of the renormalized stochastic PDE gives you a Markov process in field space. So the Markov process now lives in the space C minus 1/2 minus of M. So it's in the space of distributions. It's really a Markov process in distributions. And you can recover the Phi43 measure as a Birkhoff means here. So here is the result I drew here. You can get the Phi43 measure as a limit when computer time goes to plus infinity of Birkhoff means of your observable F. And so really your observable F is obtained as a convergent subsequence of some family of measures. Okay, thank you for your attention.
Thank you. Thank you very much, Viet, for this very nice talk. Questions? The floor is open for questions. So please raise your hand or just unmute yourself and go ahead. Let me check the chat. Okay, so since there are no questions at the moment, let me maybe kick off.
I think yeah, somebody.
Yeah, there are questions.
Yeah. Is there a question? Yeah. Oh, okay. Sorry, I don't see any. Okay, just go ahead and ask.
Okay. Hi. Can I have a question?
I think Abdel make. I cannot read your name. He was first.
Okay. Yeah. Go ahead, please.
Do you see like people raising hands?
No. Physically raising hands.
Oh, okay. Yeah. I just see the one window of so. Yes. Go ahead.
Oops. Yeah. Is there a question?
I think so.
Okay. Since nobody seems to jump in, let me start.
Yeah.
Is that okay?
Hi, Malek.
Hey. Could you explain a little bit how what is the mechanism for this uniqueness? Because I remember the lots of work in this area. Often it's just the result of tightness, and then you have basically no control on the measure that you obtain in the limit. And also I was wondering, because if you have uniqueness, then you could, for example, relate the measure in say the sphere to the measure in flat space. You could, for example, prove that, you know, if you see the flat space, you compactify with one point, you could prove a relation between the construction on the sphere and the construction on the Glim-Jaffe construction.
Okay, so what we prove here is just the tightness of the measure. I mean, in the work that we did together with Ismaël, Léonard, and Dang, we did the tightness and we proved the non-triviality of the limit. And then in the independent work, Ismaël, so based on the part of the machinery we constructed, but with some novel ideas of coupling, he was able to prove the uniqueness of the Phi43 measure. So, okay, so I'm not expert in this, so maybe Ismaël could answer, but he uses a coupling argument to say that roughly the two candidate limit measure, they charge they charge neighborhoods of some points, and since he will take two ergodic measures, they should be mutually singular. If they charge the same stuff, then they are equal. And this is roughly the argument. He proves a unique ergodicity, if you want, of the invariant measure. So this is by some clever coupling argument. This is I can send you archive reference for. So this is really but still I want to make a comment about what you said about stereographic projection. I fail to understand how you can relate the plane to the sphere, because the volume is infinite. If you pull back the volume of the plane to the sphere, you have a blow up of the volume measure at the North Pole. So
yeah,
you'd
have to modify the metric. I mean, so
yeah, but the thing is not conformal.
If you have a Phi4 model on the sphere, you can trivially produce a Phi4 model on the plane by restriction, but then it wouldn't be a translation invariant action, I suppose.
Yeah, and it's also finite volume. It's going to be finite volume on the plane.
Yes, but you can change the metric. I mean, you can pick the metric on the sphere that works for flat metric in the plane, or and vice versa.
Yeah, but if you take the flat metric on the plane, you pull back on the sphere, it has infinite volume, and I'm not sure our machinery gives you a 543 measure. You see what I mean? Like your spaces, your spaces will be weighted. You see, it's not the same Sobolev space or L2 space if you take the pullback of the plane measure, or if you take the round measure. You see, it's not the same space. So you need to work harder with a weighted space to get the case of the plane. But I believe it would be possible, but I think it's possible, but since we did not write it, I don't want to say I'm sure.
No, because for example, if you were interested in conformal transformations, that would be like simple isometries of the sphere. So it might be useful as a way to transform your measures by some non-trivial conformal maps.
Yeah, I think it should be investigated, but at this point, I'm not sure my measure has all the properties that you would like. That's what I want to say.
Okay, so, and then there was another question. Tan Nam Phan. Hi.
Yeah, hello, Viet. I'm Nam from Unit.
Hi, hello.
Yeah, thanks for a very nice talk. So my quick question is, in your last theorem, you put the same counter term that's objected from the perturbative approach, right?
It's almost like the counter term C1. It comes from the tadpole graph, and the counter term C2. It comes from the sunset. That's what I told you. Sunset is very important for us. And here I gave a slide, but you can find in the slide, if you go back home, and you see that really if you subtract exactly these two counter terms in the Lagrangian of the 543 model, you will cancel out the divergence coming from the tadpole and from the sunset in the expansion of the 2-point function. So I think, at least for Leonard and I, so Leonard is really somebody, he has a training as a physicist. It is very important for us to connect with actual perturbative quantum field theory. Even if we make a rigorous proof, we should find the same counter terms. At least it's my opinion that we should be guided by the perturbative argument. Yes.
Okay. So could I interpret the C1 something like the Wick ordering, and then C2 is non-Wick ordering?
C1 is Wick ordering and C2 is strange. C2 I'm not sure it's a Wick. I think it's not Wick ordering. It's like it's shift of the mass. It's like your theory is so bad that you have to shift the mass. You see what I mean? Like the tadpole in Feynman graph theory, always tadpole is Wick ordering. When you subtract this, the tadpole is Wick. But this one is not Wick.
Yeah.
I have to go back to physics textbook and try to see how they interpret this sunset.
Yeah, thanks.
you. Any more questions?
Maybe I can ask a question about assumptions on your construction. So
Yeah.
assumptions on the manifold, and also in this constructive part, is there an assumption on the coupling constant G?
Okay. I can slow down. Yeah, I know. The theorem is informally stated. I'm sorry. So MG is a smooth, closed, compact Riemannian manifold.
Mhm.
But what we use in smooth, closed, compact is really it's smooth and it has finite volume. That's what is important, at least for us at this level. And then there is a coupling, but the coupling here is no longer formal. In fact, the coupling can be taken to be a function. In fact, yeah, I'm sorry. If you put a coupling, then here in front of C1 you have a G. In front of C2 you have a G square, and in front of Phi43 you have a G. And you can take G to be a function. You can take a coupling function, so a space dependent, position dependent coupling. And the counter terms is really this number times G, C2 number times G square. And okay, so I think you get my point. I mean,
but can it be large? Can it be large if you scale like this?
Yeah, it can be large. We are not restricted to small couplings, unlike in the cluster expansion, for which I have amazing respect. But the cluster expansion, it seems to me you have assumptions on the coupling. It should be small.
Yeah.
In order to get things. I mean, maybe infinite volume limit, and here in these SPD methods, they have some robustness. They are not perfect. They are not amazing, but they have some robustness in the sense that my G can be large, my coupling can be large, and I still have a measure.
And maybe just last point, still related. So in your construction, do you need somehow control of the heat kernel on the manifold, or?
Oh yeah, a lot. Yeah. In fact, I use heat kernel expansion like crazy, and then I use a lot of micro-local analysis, like para-differential calculus on manifolds. You see the stuff that was developed by Bonny, Jean-Michel Bonny in the 80s. So this was tools that were devised to treat a really non-linear differential equation and study their singularities. And it was, I think it was really the input of Gubinelli, Imkeller, and Perkowski, who converted this paradifferential calculus to singular, who used it to solve singular SPDs. And we were very inspired by the work of Gubinelli, Imkeller, Perkowski, to define, in fact, our tools on manifolds. So you use heat and paradifferential calculus.
Thank you very much.
All right, any more questions?
Yes. So I have several silly questions, but this is one of them. So I'm very curious why using this stochastic quantization, the game becomes easier, at least for you. You know, so
yeah.
So this is the
I
only.
can tell you.
Yeah, okay, you know. So
I
you
can
cannot
tell you.
do this without adding this extra time, right? But,
yeah. I can tell you. I think I don't know. In fact, I think 10 years ago, I tried to do this. And I tried to open these constructive papers. And I can tell you first, from my point of view, they are hard to read. That's the first thing. Second thing, they use, it's called cluster expansion. They really cut the space into cubes. And it seems to me, maybe at the first level, because I never went deeply into them, you need translation invariance because you need cubes. They have sides. The sides are straight. You see what I mean? Like it's really translation, rotation invariant. You cut into cubes. So it didn't look flexible enough at first sight that you would be able to implement this on manifolds. And on the other hand, the SPD techniques, it relies on paradifferential calculus and stuffs that in mathematics we have the machinery. I think it's more a sociological problem. In fact, if I met somebody who is expert in cluster expansion and you work very hard, probably maybe it's possible. But I did not meet the right person and couldn't do it by the old techniques. And with this SPD analysis on manifolds, the paradifferential calculus, microlocal analysis is a well-developed field in mathematics. So we have tools to prove it. So I don't say that I can't do with the that people can't do with the old techniques, but it is true that nobody could get this measure with the old techniques, or maybe they didn't try. Maybe on manifolds is academic problem, so they don't like it. I don't know.
Very interesting. So actually, I was very close to Yonshi Wu, who invented this stochastic quantization. So I think he will be happy to hear this. Yeah. Oh, also Parisi. Yeah. Yeah. Thank you.
Yeah. Okay.
Hey, any more questions?
I have one more, if that's okay.
Yeah.
Salut Vincent. So do you see any way of getting a hold of correlation functions with this technique, or it's still far away?
It depends on what you mean. Because if you want just to define correlation function, it is possible. Because I think that these methods, they give you control on the moments. So you can define endpoint function. That's not the problem. But if your question is, you're asking me, get exponential decay of the correlation function in infinite volume, for the moment, SPD techniques do not beat the cluster expansion. Because I'm sure you know that.
What about the local analysis? So the short distance limit, for example, can you get the operator product expansion and things like that?
What I get, okay, I can tell you what I get, and you will tell me. And you'll see for yourself if you buy it or not. Phi, you can write it as this thing here, plus U, and U is C1 minus. It's not OP, but it tells you things. This has the law. This is a GFF. It tells you that any solution, the random field phi at the end, it can be decomposed at the sum of this guy, which is the GFF, minus this guy, which is C1 half minus, plus a remainder, which is nice. So you know the short distance. So as a consequence of this, for instance, you know you can guess the short distance singularity when x goes to 0, when norm of x goes to 0. For instance, you could deduce things because you know that the worst term in the expansion of phi is the GFF. So you expect that, in fact, your 2-point function, it blows up when x goes to y, let's say, it blows up at the same rate as the blow up rate for my friend, the GFF. So x minus y minus 1. Because you know the Hölder regularity, in fact, of the players in the decomposition. I think this is something cheap that the SPD method gives you access to. But the OPE is much more ambitious. It is like asking asymptotic expansion. And for the moment, from what I understand from SPD, I don't know how to get OPEs.
You mean you cannot push the expansion past the first term? You cannot get the next?
Yeah, because U, at least to my knowledge, because U is solved by using fixed point. But I mean, to be honest, I don't know many constructive theories where you can prove the OP. For instance, for Phi2, I'm not sure you can prove the OP. Phi2, where you don't need the SPD stuff, you just do Nelson bounds. I'm not sure you can prove the OP. In fact, the OP is just like an axiom when you do CFT, but in actual QFT, proving the OP beyond perturbation theory is very nice open problem, even for very simple theories. I don't know if you agree with me or if I'm too pessimistic.
Yeah, I don't know.
Okay, so maybe it's time to finish the official discussion and we can continue a bit afterwards. So thank you very much, Viet, for this lovely talk. And yeah, thanks everyone for coming.